you all to this webinar on Make Things IoT Ready. Just a few ground rules before we begin. I hope everybody can hear me very clearly. If you have any issues, please use the chat window, and we'll try and solve that. Because we have a lot of joinees here, all of you are muted by default. So while I welcome questions throughout this talk, please use the chat window to send in your questions, and I'll take them up one by one at the end of it. So, hi everyone, my name is Ranjit Nair. I'm the co-founder and CTO of Altizon Systems, and today we're going to talk about making things IoT ready. So, a little bit about me before we begin. So this is hopefully going to be a technology talk more than anything else. I'm the co-founder and CTO of Altizon. We started this company back in April 2013, and I'm building Altizon's product called Dataness, which is a highly scalable platform for the Internet of Things. And hopefully I can share some of the insights that I've gained while building this product out over the last 18 months. So I play around with technology, much to the frustration of engineers who use excessive technology. That is a complaint I've heard very, very often. I've written a lot of my programming in Java, and I use a bit of other technologies at this point in time. In my spare time, I love to ride my old motorcycle. Put a picture in there so that everybody can see it. It's one of the greatest motorcycles in the world. And I love traveling and taking photographs in my spare time. So that's me, and yeah, I still write code every day, which is pretty cool. Before we begin, IoT is the Internet of Things, very pervasive phase at this point in time. Probably, I've seen graphs which described at the top of a hype cycle. And what does it really mean? And I want to take 5 minutes to explain my perspective about why does IoT exist and why is everybody talking about it at this point in time? I once met a very interesting gentleman who once told me that, hey, IoT, it's been around since the time of Nikola Tesla when he invented wireless communication. But that is kind of a myopic way to look at it. It is not just that, it's a lot beyond that. And it has got a lot to do with the way technology and the entire industry has matured over the last 50 years. If you try to break it down, IoT is kind of IT in a sense. With the advent of the personal computer almost 50 years ago, you suddenly had the power of desktop, and it impacted individuals. So, activities that were manual, started to get automation. That was the first wave. So things like order processing, bill paying, computer-aided design, stuff that you had to do by yourself. Was the first set of things that got automated by IT, and it brought about a huge amount of process gains. The second wave came in with the rise of the internet. So, in a sense, these individual processes that would exist started getting connected, and a lot of coordination started to be made amongst these systems. Distributed supply chains and enterprise resource planning systems. These were systems that used to talk to each other and basically took individual and got them connected. That was the next big wave. I think the third wave of IoT is all about the product itself. What IoT really means from my perspective is information technology being an integral part of any product that you go ahead and build. And what is driving this innovation is embedded sensors, cheap processors, computers going inside, products. You can find new products into which cheap computers go in, which have great computing and storage resources. And then, this is backed up by, the advent of the cloud, with the ability to deal with large amounts of data, with the ability to, collect and analyze massive amounts of data. So, this is given rise to critical mass for IoT. Altizon has worked with customers where we can really see how pervasive connectivity exists at this point in time. A customer of ours wants to analyze power quality in extremely remote villages in India, and we all now know that in India the growth of mobile networks has far outstripped pretty much everything else out there. Everybody has a mobile phone in their hands, and data networks are growing almost continuously. So there are wired and wireless data networks everywhere, which means that data can be driven back uh, to the cloud. In a sense, for telecom companies as well, it has been extremely profitable to have data networks go out there. There are only 6 billion humans in this world, but several billion things that can possibly get connected and send data over data networks. So a huge push has been, ubiquitous data networks everywhere. The second big enabler for kind of enables IoT is a lot of focus and emphasis on improving computing on the edge, simpler, cheaper computers that can be embedded into any product. And an advent of this is the interesting system-on-chip boards that you see all around you these days. A great example of that was the Raspberry Pi board. It's a $25 board that allows you to build small enough-spaced applications on top of it, primarily meant aimed at education in the poorer regions of Africa, but suddenly, with Intel stepping in with the Galileo, you're suddenly starting to see full-fledged, small, cheap system-on-chip boards with modern operating systems running on it, which gives you a lot of flexibility in terms of computing on the edge. And then the third one has been the rise of Amazon Web Services and the cloud as we see it right now. You can go to AWS, swipe a credit card, and you can get servers up on demand, and then you can keep increasing your server farm as you go along and have the ability to deal with massive compute and massive storage, which means that as connectivity explodes, as things on the edge starts getting intelligent, as processing power, and starts to send data back on these data networks, you also have simplified systems that can be built on top of the cloud that can grow exponentially based on the data coming in and can process and store this information at scale. A second more important thing, and I'll deal with that as I talk about the technology stack, is databases to deal with unstructured data. You have newer and newer things with different data sets being connected and pushing data onto the cloud platform. And there has been a massive shift in NoSQL databases, which can deal and process unstructured data at scale. And the third one, of course, is Hadoop and its family of platforms like Spark, which allows you to process massive amounts of data at scale, petabyte data at scale. So, a shift in IT, the advent of intelligent products, as well as the shift in technology, which allows connectivity, great computing on the edge, and the ability to deal with large amounts of data. All of this coming together has resulted in IoT gaining the kind of eyeballs that it does. I think it would have been a little too early 5 years ago, but now the time is right in all of these respects. So if you get started and say, hey, I want to go ahead and start building a smart connected product, which is essentially the topic of this talk today, what does it take to do that? I think before we get there, there are two fundamental questions that need to be asked. Are you trying to build a smart connected product from scratch, or do you have an existing product that can do with connectivity that has always existed for several years, perhaps several decades? And can connectivity and intelligence be transported on that device, make it available, plugged in to that device? I think it's important to address both of these areas. So I think it's relatively simpler if you're thinking about building smart connected devices and products from scratch, because newer chipsets and newer ability to deal with sensors has made this a lot simpler. If you see this image on the left, it's a classical example of how intelligence has gone down to the sensing element level. Nibelium produces connected wireless sensors. So you could connect, for instance, a temperature sensor, a pressure sensor, or pretty much a proximity sensor, pretty much anything you wish, onto a little chip which transmits wirelessly, and all of this information can be collected. So suddenly you have intelligent connected sensors that you can build on top of it. But what about an old machine? Let's say you're going to walk into a factory floor and you're looking at a 20-year-old machine, which is very expensive and it's critical for operation, but it's entirely mechanical and relay driven. how do you make a machine like that intelligent? How can the machine report back to you about what it's currently doing? So there's a whole suite of connectivity options that are also coming up there. An example of that is this element that you see on the right, which is an export Profinet device that is built by a company called Grid Connect. What that allows you to do is to interface serial ports, to interface relays, and make this information available over TCP. So with that, intrinsic information that exists within the machine itself is now available outside, and you can start collecting and looking at that information. A simple example of this application would be if you walk into a factory floor, in any manufacturing plant, and you look at a machine, and the machine operates all day long. If you want to know, hey, what has my machine done all day long? The machine will probably not tell that to you. But using these options, these over-the-counter solutions and applications and hardware, you can interface with the machine. The machine can start giving information that it held back, and then you can build connectivity solutions on top of it and have this data stream to the cloud. So technologies exist to enable your smart plants as well as to try and make your old dumb connected machines smart. Another very important thing to consider is fine. I suddenly have a machine and I can start talking to it, sensing elements. I'm getting sensor data from the edge. What do I do next? A very important point to consider at this point is you need to have some form of processing power at the edge itself, because you do not want to stream all kinds of information to the cloud, because probably your system is too chatty. A lot of the data is irrelevant. Possibly 90% of the data is irrelevant. You want to do some processing on the edge, which makes your systems inherently more scalable. For instance, you could be connecting to a machine. The machine is sending you 150 parameters, but you're only interested in 3 of them, and you want to aggregate them at a microsecond level and try and push this information to the cloud. So there are many scenarios where you would want reasonable computing resources on the edge. And the advent of the system on chips kind of boards has enabled you to build these, I would really call them gateway devices. So devices that enable connectivity from sensors to the cloud. And these system on chip computers have made that possible. A traditional way of how you build that kind of intelligence on the edge was to use a board that is highlighted with the Neptune and STM32 Cortex M4 chip, a traditional hardware embedded chip. These chips are available for a few dollars over the counter, and you can start using them. And now we have the successor to these kind of chips, like the Intel Calivio, the Raspberry Pi, the BeagleBone. What is the big difference between both of these kind of elements? I think you could technically achieve connectivity using both these kind of chips. You really don't need an SoC. But what SoCs have done is democratized the entire stack for you. Traditionally, computing chips that sat on the edge were not really connectivity oriented. For instance, I spent a couple of weeks trying to get the Cortex M4 chip work, over a GSM modem, and it was hard to do it. It took me back several years in terms of the technology stack itself. And you need deep embedded expertise to build these kind of devices out there. However, the modern chipsets come with a full-blown operating system. For instance, Galileo, has an Arduino board built on top of it, and it can run Linux. The Raspberry Pi runs a version of Debian Linux. And Linux comes with its own set of libraries and drivers and existing code. And people have built a ton of frameworks and applications and components on top of it, which do a variety of things for you. Certainly, this, by providing compute on the edge, which runs a full-blown operating system and partial to Linux, opens up the entire ecosystem of platforms and components and utilities that developers have spent years writing on top of Linux, and all of that is available to you for free. Let's say you want to do large-scale text parsing on the edge from all the sensor data that's coming in, that is possible. You want to run a small little embedded database on the edge, which will cache data and deal with network outages and connectivity. That is available as a standard reusable component. So you're essentially going up the stack by using more modern programming languages like Python and Java to program these elements, and that just makes embedded programming and development so much faster. Puts power in the hands of the masses instead of you having to be a specialist embedded system designer. The third part